Binary acids, oxoacids, and polyprotic acids are going to be the topics of this lesson. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, in addition to high school and college science prep, we also do MCAT, DAT, and OAT prep as well. I'll be sure to leave links in the description below for where you can find those courses. Now, this lesson is part of my new general chemistry playlist. I'm releasing several lessons a week throughout the school year, so if you want to be notified every time I post a new lesson, subscribe to the channel, click the bell notification. All right, so we're going to start with binary acids. We're going to talk about trends in acid strength for these binary acids. And in this case, you first got to understand what is a binary acid. Well, a binary acid, and if you think of that word binary, the prefix bi is on the front there, which means two. A binary acid is typically one that's going to be composed of exactly two elements, hydrogen and one other. Now, it turns out there are some exceptions to that, like HCN is technically a binary acid, so, but it's not one we're actually going to even discuss. So for you in this lesson, you're probably, again, the only binary acids you're going to see are going to have two elements, hydrogen and one other. So in this case, the most common ones are going to be the hydrohalic acids, HF, HCl, HBr, and HI. So however, water technically could be classed as a binary acid. And so when I say it has exactly two elements, I don't mean that it necessarily only has two atoms. So you're going to have, some variable number of hydrogens and then one other element. So cool, so these are our binary acids, and turns out an explicit trend for their strength. And that first part of that trend is they're going to increase as you go down a group. And it turns out that's going to be related to size. And so size, it turns out, is the most important factor for determining the strength of one of these binary acids. And it turns out it's related to the fact of how long the bond is. So bond length is defined as nucleus to nucleus distance here. So if I went from nucleus of hydrogen to nucleus of some other atom, so it turns out the longer that bond is, the weaker that bond is. And a weaker bond is going to dissociate more. And so we talked about the difference between strong acids and weak acids in the last lesson. And a strong acid dissociates 100%, whereas a weak acid is only going to dissociate partially, often less than 5%. And it turns out, in terms of relative strengths, the more an acid dissociates, the stronger we say that acid is. And so it turns out longer bonds are going to dissociate more, resulting in a stronger acid. And so that's why they increase in strength as you go down a group. So it's all about increases in size, weaker bonds, and greater dissociation. However, it's also going to increase from left to right as you go across a period. And this one's going to be a little bit strange, but it's not about size. So it turns out when you're in the same period, you're going to have some, changes in size, but not like when you go down a group and stuff like this. And because you don't have such large differences in size, well, then the second most important criterion becomes the most important one for this comparison. That's electronegativity. Cool, and as you get a more electronegative atom as part of your binary acid, it turns into a stronger acid. And again, both of these trends, you probably know these if you've already, from the last lesson, memorized your strong acids. If we look at, going down a group, HF is not a strong acid, but HCl, HBr, and HI are strong acids. So if there's a trend, it must be increasing strength as you go down. Well, same thing here. You probably know that HF now is a weak acid. Water you'd probably consider as neutral. And then NH3 we learned was a weak base. And so going across for our binary acids here, we go from a weak base to a neutral compound to a weak acid. We're definitely increasing in acidity as we go to the right. And so in this case, it turns out it's not about the size of the bond or the length of the bond or anything like that. It turns out it's actually the stability of the conjugate base. So if you look at HF, when he dissociates, you get his conjugate base right here. So and you find out that one of the best ways we have for comparing acid strengths is actually looking at the stability of the conjugate base instead. And so in this case, the conjugate base has a negative charge, and it turns out a negative charge is more stable on a more electronegative atom. We saw this when we drew Lewis structures, and we had to compare like some certain resonant structures on occasion and stuff. So, and in this case, then, any one of these three, when they dissociate, is going to have a negative formal charge either on fluorine or on oxygen or on nitrogen. And if I had my choice, I'd prefer to have that negative charge on a fluorine. It's more stable when it's there. Well, it turns out a more stable base is a weaker conjugate base, and it turns out there's always this inverse relationship. The stronger an acid, the weaker its conjugate base. The stronger a base, the weaker its conjugate acid. And so here, if fluoride here is more electronegative than either nitrogen or oxygen, then this fluoride conjugate base is going to be more stable than either of the other two. And a more stable base is a weaker base, and a weaker base comes from a stronger conjugate acid. So we'll find out when we talk about the oxoacid trend in a little bit, we're going to allude back to this kind of a thing where we relate, stronger acids have weaker and more stable conjugate bases. So, and there's also this, always this kind of inverse relationship between stability and reactivity. So something that is more stable is less reactive. So an increase in stability is always going to correspond to a lowering say this right. Increase in stability is going to be lower reactivity. And so if you're stable the way you are, well, then you don't want to change. And if you don't want to change, well, then you don't want to react to become something new. It's kind of the way to think about this. So, but for binary acids, you're definitely going to have to know this trend. But now based on what we just talked about with the stronger an acid, the weaker the conjugate base, well, now they can ask you about a trend for the conjugate bases too in a question. So if I gave you 4 conjugate bases here, and I gave you I minus, Br minus, Cl minus, and F minus, and said, which one is the strongest conjugate base? Well, again, the trend we learn is for acidity, and that's really the trend you need to memorize. So if you're looking at the conjugate bases, well, again, the stronger the acid, the weaker the conjugate base. So if I want the strongest conjugate base, well, then I want to choose the one that's the conjugate base of the weakest acid. And so for these guys with their conjugate bases, the weakest acid is HF. And so HF, being the weakest of these 4 acids, would have the strongest conjugate base. And so you find out that the trend in basicity for the conjugate bases is exactly the opposite trend we saw for their corresponding conjugate acids. All right, so now we'll move on to these oxoacids, also called oxyacids. An oxoacid has 3 elements. Well, they're acids, so they have hydrogen. They're oxoacids, so they also have oxygen. And then they have one other element that I'm just going to call the hetero atom or the hetero element, just the other one. All right, so there's 2 parts to this trend for oxoacids, and it turns out more oxygens, more acidic. And so if we take a look here, we've got HClO4 on top, HClO3 right below it. And then we've got here ClO4 minus the conjugate base and ClO3 minus the conjugate base. And so it turns out when we look at these oxoacids, so we're always going to kind of look at the strength of the conjugate base. And so it turns out with these oxoacids, we're going to find out that the length of the bond never comes into play like it did with the binary acids. Because in an oxoacid, the acidic hydrogen is always bonded to an oxygen. It's never bonded to that hetero atom, that other element, in this case chlorine, and for both of these examples. So it turns out then we're going to be reliant on looking at the stability of the conjugate base. And a more stable conjugate base, again, will be a weaker conjugate base. And a weaker conjugate base comes from a stronger conjugate acid. All right, so if we take a look at these conjugate bases, we've got the perchlorate ion, ClO4 minus, and the chlorate ion, ClO3 minus. And the difference is that extra oxygen. Well, what difference does that make? Well, all the difference in the world, it turns out. So turns out if I was going to ask you to draw the proper Lewis structure here, I'd include some more lone pairs, and I actually included those on the study guide. So all the oxygens got some lone pairs here and stuff like that. So I didn't want to get bogged down with the details, but the big thing I want to show here is that this lovely structure actually has 3 additional resonance structures. I could make any 3 out of the 4 oxygens have a double bond, and then just one have a single bond with the negative charge on that oxygen. And so as a result, all 4 of these oxygens get a chance to share that negative charge. Well, negative charge is an indication that you have too many electrons. And it turns out, for stability purposes, you don't want to have too many electrons, you don't want to have too few electrons, you want to be as close to neutral as possible most of the time. And so in this case, negative charge means you have too many electrons. That kind of takes you away from stability. But at least you're sharing that negative charge with 4 oxygens total, so that each one only really is bearing a 1/4 of that negative charge. Whereas with ClO3 minus, you're only going to have 3 resonance structures, with the negative charge only being shared between 3 oxygens, so that each of them has negative 1/3 of a charge, if you will. And so typically the more atoms you can share that negative charge with, in this case the more oxygens, the more stable it's going to be. And so ClO4 is a more stable conjugate base. That makes it a weaker conjugate base, and a weaker conjugate base comes from a stronger conjugate acid. So the first part of the trend, more oxygens, more acidic for these oxy or oxoacids, and it really comes down to resonance stabilization of that conjugate base. All right, so the second part of this trend here is the more electronegative heteroatom, the more acidic. So I wrote them in this order because usually the greater number of oxygens is the most important thing. But what if both your acids have exactly the same number of oxygens, like HClO4 and HBrO4? Well, then what do? Well, that's when you go here, and more electronegative heteroatom, more acidic. And big thing here is that for the heteroatom, its size does not matter like it did with the binary acid. It's purely about its electronegativity, no ifs, ands, or buts. It doesn't matter if you're comparing things in the same group or in the same period. It is all about electronegativity, nothing about size. All right, so we see what's going on here. In both cases here, we're going to end up with 4 resonance structures. You're going to have that negative charge shared by 4 oxygens. No difference there. So rule number 1 doesn't help us. We move on to rule number 2. Well, then it goes, how electronegative is that heteroatom, in this case, that central atom, chlorine versus bromine? Whichever one is more electronegative is going to give you a stronger acid. Well, you might recall again, fluorine's the most electronegative element on the periodic table, and so chlorine is more electronegative than bromine, and as a result, if I had to pick the stronger acid, I'd definitely be picking HClO4. Now, you probably already knew this, though, because HClO4 is on the strong acids list, and HBrO4 is not on the strong acids list. So if one of them is stronger than the other, it's probably the strong one that's stronger than the weak one. All right, and how do we explain this? Well, if you look at this, electronegativity gives you the ability to pull electrons towards you through the bonds. We learned this with like polar structures and things of this sort. And so what's happening is chlorine is actually pulling electron density away from those oxygens more than bromine is. And by pulling electrons towards them, chlorine's taking on a little bit of that negative charge and making all 4 of these oxygens a little less negative themselves. And so it spreads out the negative charge even more. And we said the more atoms that are sharing that negative charge, then the less of that burden all of them are bearing and stuff like this. So super important in this case. And so it turns out chlorine's ability to pull electrons towards him, though, again, has nothing to do with his size, everything to do with how electronegative he is. And that's why HClO4 ends up being a stronger acid than HBrO4, because his conjugate base is more stable. Now, the reason we give to this is what we call the inductive effect, or simply induction. So if you're pulling electrons through the bonds due to your electronegativity, that's induction, or the inductive effect here. So rule number 1 was all about resonance stabilization of the conjugate base. So rule number 2 is about inductive stabilization of the conjugate base instead. Now, one thing to note again is, I just want to emphasize this, really important, is that this had nothing to do with size. You might have been like, wait a minute, Chad, you just told me a minute ago that HCl versus HBr, you told me that HBr was stronger, and it was due to its size. You're right, I did. And that's when we were talking about binary acids. But now we're talking about oxoacids, not binary acids. And for an oxoacid, size is irrelevant. And again, why did we say that HBr was stronger? Well, it was due to its size was relevant because that was the size of the bond to the hydrogen. And HBr had that longer bond, and a longer bond was a weaker bond. Well, with an oxoacid, again, that hydrogen is never bonded to the chlorine or the bromine. For an oxoacid, hydrogen is always bonded to oxygen. And so that means the length of that bond is roughly the same in either case, and size doesn't come to play a role, the size of the chlorine or the bromine. So hydrogen's not bonded to them. And so the only quality for chlorine and bromine for an oxyacid that is relevant is its electronegativity, its ability to carry out inductive stabilization here. Its size doesn't affect the length of the bond to the hydrogen at all. Cool, so I just want to make sure you see this difference. So if you're comparing binary acids, they get stronger as you go down a group. But if you're comparing oxoacids like we're here, they're actually getting stronger up the group. One is based on size for binary acids. The other is based on electronegativity only for our oxoacids. Hopefully you can see that difference. So let's take a look at polyprotic acids. All right, polyprotic acids. So a polyprotic acid is an acid that can act as a proton donor more than once. So we've got phosphoric acid here, and it turns out phosphoric acid has 3 acidic protons, definitely a polyprotic acid. And then sulfuric acid is the only one of our strong acids that is a polyprotic acid. All the rest we'd call monoprotic. So but he's polyprotic, he's got 2 acidic hydrogens here. All right, so the big trend with polyprotic acids is it turns out as they donate H's, it gets harder for them to donate successive H's. So if you notice here, we're going to donate an H, and that's going to result in a species that is now negatively charged. And so it's more attracted to the H plus ions that are still attached to it, which makes it harder to give them away. And now he's got a -2 charge, and so the one he's got left, he's even more attracted to it, and it's even harder to give him away. And so their proton donation, they get less and less acidic as you go down the chain in this what we call a polyprotic acid series. So we'll find out their equilibrium constants to describe acid strengths. So, and the more they dissociate to form products, the greater these equilibrium constants are going to be. And so what we're going to find out that is if these are getting less and less acidic as we go along, their equilibrium constants are getting smaller and smaller and smaller. So each successive H plus ion donation, proton donation, is going to have its own equilibrium constant, and they get smaller as we go. And we'll see that in a couple lessons. All right, so now we've got it with a strong acid as well. And in this case, what you should know about sulfuric acid, only one of the H's is strong, the other one's weak. And so only the first donation goes to completion effectively. So donation of that second proton, again, it gets weaker and weaker as you go. So the first one went strong. We shouldn't be surprised if the second one is donated to a smaller extent, in this case, only as a weak acid. So we get 100% dissociation for the first part, and probably less than 5% for the second part. All right, so some things you should realize here. So if we look up at the weak acid, so with our weak acid, again, because he's weak, he probably is going to dissociate less than 5%. Let's say it's 1% or something like this. Well, the 99% is going to stay looking like H3PO4, and 1% is going to turn into each of these. And so, we're going to have this equilibrium established between all these species, but most of it's still just going to be in the form of H3PO4. It's going to be the most abundant species in your solution. So, but after that, you'd figure, well, you're probably going to have equal amounts of H plus and H2PO4 minus. And you might think that, except you don't. So if none of the rest of this existed, then that would be true. It's a 1-to-1 ratio. However, because you get a little bit further dissociation, so of the H2PO4 minus, one, it's going to form a little more H plus. So this concentration is actually going to go up, but it actually uses up the H2PO4 minus, so his concentration is going to go down. And so as a result, these aren't going to end up being equal in the end. The H plus concentration is going to be a little bit greater than that H2PO4 minus. But again, it's going to get less acidic though. So if 1% of the H3PO4 dissociated to give us a tiny amount of this, 1% essentially, well, again, only maybe say 0.01% of this is now going to dissociate. And then maybe 0.0001% of this would dissociate. It gets much less acidic going along the way here. And it's usually quite a bit less. I might even be understating it. So next on the chain then would be the HPO42 minus. You're going to have a lot less of him than of that H2PO4 minus. And then even less at the end of the chain here is going to be the phosphate, which you'll have the smallest amount of. So, and these kind of relative concentrations are something you should kind of realize. Now, in the case of H2SO4, we might think, oh, okay, I know how this works then. So I'm going to have the greatest amount of H2SO4, and then I'm going to have H plus. So, and we would think that initially these are equal, but some of him is going to go away and it's going to create some more H plus. So actually the H plus is greater than the HSO4 minus. And then finally at the end of the chain is the concentration of SO42 minus, except we have a problem here. We started with a strong polyprotic acid, not a weak one like we did here. For a weak acid, it dissociates less than 5%. And we said, well, maybe how about 1%? So 99% stays looking like this. But H2SO4 is a strong acid. How much does he dissociate? 100%, which means how much H2SO4 is left in your solution? Well, effectively 0. Now, the truth is it's not exactly 0, but it's pretty darn close to 0. And so way down at the other end, that's where the H2SO4 is now. So if you're asked to kind of, show some relative, concentrations of species in the solution, you should definitely take that into account in the case of H2SO4 being a strong polyprotic acid. So, but this is kind of what to be aware of. And notice in the middle of these polyprotic acid trends, that's where you find your amphoteric compound. So H2PO4- is amphoteric. He can act as an acid going to the right, or he can act as a base going back to the left. He can donate a proton, or he can accept a proton. He's amphoteric. So is the HPO42-, and so is the HSO4-. They're all amphoteric species, and that's what you often find in the middle of any of these polyprotic acid series. Cool, get your calculators handy because in the next lesson we're going to have a little fun with the pH scale. So if you found this lesson helpful, so hit that thumbs up button. Best thing you can do to support the channel and let YouTube know that other students need to see this lesson as well. And if you are looking for practice problems on acids and bases or anything else in general chemistry, check out my General Chemistry Master course. I'll leave links in the description. A free trial's available. Happy studying.